Good morning. We are the Black Bulls team, integrated by Martínez Galindo Alberto, Galván Pacheco, Ángela Odisei, Castañedo Olvera Jonathan, Guzmán Olivera Bernardo, Enrique Zamora Sergio, and I, Gutiérrez Gaitán Cesar Emiliano, and we are going to present you our first experiences with the operational amplifiers.
Okay, let's start with a little introduction. The operational amplifier is designed to solve mathematical operations, so as adding, subtracting, and integration and differentiation. Well, that's why the operational in the name. Uh, the next one, please. Okay, now the new ones, the new operational amplifiers are now the one that we already know, the integrated circuits that now has upgraded and works with lower voltage, and they are available in a variety of specialized forms. Now, obviously, there are some advantages that we must mention, so as the lower cost, the versatility, and the dependability.
Operational amplifiers have five basic terminals, two for supply power and two for input signals, and only one for output. Next, please. The ideal operation amplifiers has infinite gain and input resistance, but output zero output resistance. We can see here the equation. Next, please. Operational amplifiers terminals labeled positive voltage and negative voltage identifies those operation amplifiers terminals that must be connected to the power supply. Here we can see here the typical schematic representation of supplying power to an operation amplifier. Output impedance is 0 ohms and the power supply's voltage are without limit. We now examine the function of each operational amplifier terminal to understand something about the limitation of a real operation amplifier. Next, please. The people who design and build operation amplifiers have done such an outstanding job that external components connected to the operation amplifier determine what the overall system will do. Since there is only one output terminal in an operation amplifier, it is called a single-ended output. Most of the operational amplifiers have internal circuitry that automatically limits current drawn from the output terminal. Here we can see that there is only one output terminal, so this is why it is called a single-ended output. Next, please. The operation amplifier's output terminal is connected to one side of the load resistor and the other side of the resistor is wired to the ground. Output voltage is measured with respect to the ground. Since there is only one output terminal in an operation amplifier, it is called, as I said before, a single-ended output. There is a limit to the current that can be drawn from the output terminal of an operation amplifier, usually on the order of 5 to 10 milliamperes. Mm, yes, this one. Most of the operation amplifiers, like the 741, have internal circuitry that automatically limits current around from the output terminal. Even with a short circuit for resistances, output current is limited to about 25 milliamperes. This feature prevents destruction of the operation amplifier in the event of a short circuit. Next, please. No, back. Back. Yes, that one. There are two input terminals labeled negative and positive. They are called differential input terminals. because the output voltage depends only on the difference in voltage between them. We conclude that the polarity of the output terminal is the same as the polarity of positive input terminal with respect to the negative input terminal. With this, it is important to emphasize that the polarity of voltage, output voltage, depends only on the difference in voltage between inverting and non-inverting inputs. Next, please.
I'm going to talk about the open loop voltage gain. Okay, let's start with the definition. The output voltage that is represented with EO is determined by ED, that is the differential input voltage, and, and the open loop voltage gain. AOL is called open loop voltage gain because possible feedback connections from output terminal to input terminals are left open. Accordingly, the BO is expressed by the next relationship. And here we can see the formula of the output voltage, that is output voltage. It's well, here we can see the relationship that says that the output voltage is equal to the differential input voltage that is equal to the open loop gain. And down we can see the relationship expressed with their corresponding letters. Next slide, please. Okay, the differential input voltage, or the ED. The value of the open loop gain is extremely large, often 200,000 or more. The the output voltage can never exceed the positive or negative saturation voltage, that plus saturation voltage and minus saturation voltage. For a plus minus 15 volts supply, the saturation voltage are approximately plus minus 13 volts. And here we can see the formula. Well, the formula for the ED maximum is ED maximum equals to plus saturation voltage over the open loop voltage, and for the minus ED maximum, the formula is minus ED maximum equals to saturation minus saturation voltage open over the open loop gain. Next slide, please. The conclusions. We have two conclusions. There are two conclusions to be drawn from these brief comments. First, we have that the output voltage either will be at one of the limits, mm, plus saturation voltage or minus saturation voltage will be oscillating between these limits. And second, we have to maintain the output voltage between these limits, we must go to a feedback type of circuit that forces the output voltage to depend on stable precision elements such as resistors and capacitors.
Now, the zero crossing detectors. We are going to talk about the non-inverting zero crossing detectors and the inverting zero crossing detectors. First of all, the operational amplifier operates as a comparator, the one that we can see at the first image. Well, its input, its positive input compares voltage EI with a reference voltage of 0 volts. And well, when EI is above Vref, V0 is going to be equal to positive Vsat. Now, the reason of this is because the voltage at the positive input is more positive than the voltage at the negative input. In this way, the sign of ED in the image, it's going to be positive, and consequently, VO is going to be positive also. Let's say that the polarity of VO tells us if EI is above or below Vref. The transition of VO tells when EI cross the reference and in what direction. Now, the inverting zero crossing detectors. Uh, the operational amplifier input compares EI with a reference voltage of 0 volts as in the first image, but in this time we have that the input that makes this is a negative input. Uh, okay. Well, the previous image tells us that this circuit is an inverting zero crossing detector. The wave shapes of VO versus time and VO versus EI in the image can be explained in a certain way. First, if EI is more positive than Vref, then VO equals to negative Vsat. And secondly, where EI crosses the reference, going positive makes a negative going transition from positive Vsat to negative Vsat. Well,
In zero crossing detector circuits, the reference level with which the input signal is compared is zero. However, it's possible to compare the input signal with a non-zero reference level that allows to think of a better detector with a positive level and negative level detection circuit. In this case, we have here a non-inverting positive voltage level detector. In this circuit, the input voltage is compared to a positive value of voltage when the input voltage is greater than the reference voltage that we set. The input voltage will be equal to the positive saturation voltage. And as we know, this value of saturation voltage is slightly lower than the input voltage. The next, please. As I told you before, these graphs show us that for voltage level higher than the reference voltage, the value in the output will be equal to the positive saturation voltage of the op amp. Next one, please. And in the opposite case, where the input voltage is less than the established reference voltage, when then the input voltage will be equivalent to the negative saturation voltage. In this case, is like the opposite values in the input. So the result will be with the opposite signal. In this case, is negative. You can see here in the signal we have E1, that is our value of input voltage, and the voltage of reference in the peak of our voltage input is greater than the voltage reference. We have the value of the saturated voltage as a negative value. So now we have here a non-inverting negative voltage level detector that the input voltage is compared with a negative reference level voltage. And when the input voltage is greater than the reference voltage but in negative, the output voltage will be the positive value of the saturation voltage of the op amp. And as you can see in the picture, when the value of the input signal voltage is bigger than the reference voltage, the value in the output, it will be equal to the saturation voltage. But in the moment that our signal of input is lower than the reference signal voltage. In this case, the value of the output will be equal to the saturation voltage, but in negative. Now we have a non-inverting negative voltage level detector circuit, and when the input voltage is compared with a negative reference voltage level. So when the input voltage is greater than the reference voltage in negative, the output voltage will be with the positive saturation voltage value of the op amp, but instead of the input voltage is less than the negative reference voltage, in this case, the output voltage will be equal to the negative saturation voltage. As you can see, when the value of the voltage input is bigger than the negative value of reference voltage, the value in the output it will be equal to the negative saturation voltage. But when the value of the input voltage is less than the negative reference voltage that we set, the value in the input will be equal to the value of the saturation voltage in positive.
Well, I will talk about a typical application of voltage level detectors. Adjustable reference voltage. The integrated circuits are able to set precise voltage reference. As we can see in the image A, if the signal or source is applied to the positive input, the circuit action is non-inverting. On the other hand, in the image B, if the signal source is applied to the negative input, the circuit action is inverting. Next, please. A zone-activate switch is made by connecting the output of a non-inverting voltage level detector to an alarm circuit. The procedure to arm the zone switch is as follows. Open the reset switch to turn off both SCR and alarm. In a quiet environment, adjust the sensitive control unit output voltage. Use swing to saturate voltage. Close the reset switch, the alarm should remain off. Normally, the operation of some activate system is based on an amplification of the received signal, which after performing the sensitive control is transformed into a continuous signal of sufficient level to exceed a relay to perform the switching. Next, please. Light column voltmeter displays a column of light whose age is proportional to voltage. They are easy to read at distance. That is to say that each LED is going to be lit according to the level of continuous voltage present in the input. So if we had 4 LEDs calibrate for step of 1 volt per LED and 3 LEDs were lit, we would say that the input is greater than 3 volts and less than 4 volts. Next, please. Smoke detector. It works through a lamp and a photoconducting cell that are inside a closed chamber that emits smoke and dust but no external light. So when a dust particle enters the chamber, causes light the reflect of the particles and hit the photoconductor. This causes the resistance to decrease and the voltage to increase by triggering the alarm. Some smoke detector systems contain as SCR resistor, which are typical of electronic switch that allows the alarm to remain once activated. That's it.